Welcome to our presentation on Bioclimatic Design Form. I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte's Ravin School of Architecture. We will discuss how architectural form becomes a tool for bioclimatic design. There are many books available on bioclimatic design. These books are recommended for those interested in exploring the topic further. We discussed the net zero design approach in the zero design videos. The net zero energy approach on the left consists of bioclimatic design, energy efficient systems, and renewable energy integration. The design goal is to reduce energy use through bioclimatic strategies and energy efficient building service systems. Then, the on-site renewable energy system is integrated to support building operations. The net zero carbon approach on the right requires additional strategies beyond the net zero energy approach. Net zero carbon strategies include the use of renewable, bio-based construction materials and the integration of vegetative systems, both of which offset carbon emissions from the building overall. The final performance goal is to design buildings that achieve both net zero energy and net zero carbon. For more information, refer to the additional videos indicated in the slide. In summary 1, bioclimatic design is a fundamental step toward net zero building design strategies that utilize climate and site resources to create a healthy, energy-efficient built environment. 2, bioclimatic design enhances occupant comfort, health, and well-being through natural ventilation, shading, daylighting, and moisture control. 3, bioclimatic design minimizes the use of active building systems and reduces energy consumption in heating, cooling, ventilation, and lighting energy. 4, bioclimatic design preserves natural resources while protecting surrounding ecosystems, such as bodies of water, vegetation, and natural habitats. Slides 3 through 5 introduce building forms tailored to their climates and site conditions. They show how building mass, orientation, and program requirements help harness natural resources for better comfort and efficiency. For example, the interaction between the building, climate, and site influences the building's size and shape. The key point is that by smartly tuning massing, orientation, and layout, the form of the building itself becomes our first layer of climate control, manipulating sun, air, and moisture to naturally create more comfortable conditions. Here we delve further into how tweaking orientation and shape alters the building's interaction with climate, resulting in energy savings expressed in percent. In effect, the design acts like a device that either invites or deflects natural forces. For instance, if we align a long building east-west, its broad sides face north and south, meaning they get more gentle indirect sunlight and less of the glaring east-west sun. The message is that strategic form decisions like where a courtyard or stepped terrace are placed can prevent overheating and improve ventilation without any mechanical intervention, just through the building's positioning and shape. Certain building programs have benefits from sunlight and air. For example, library and workshop spaces perform better to have north-facing windows and bring diffuse light in for reading and detailed tasks. Bedrooms should avoid facing western windows due to visual glare and heat buildup during sunset time. Kitchens should be located in areas where direct sunlight does not come deep inside, and operable windows are available for natural ventilation to remove cooking odors and moisture. Now we shift focus to dedicated shading devices as a strategy for natural cooling and solar regulation. This slide defines what we mean by shading devices and introduces the concept of a shading mask. Essentially, any element attached to building surfaces that obstructs the direct line of sight to the sun can serve as a shading device, such as eaves, overhangs, brise soleil fins, screens, and the like. Each such device covers a certain portion of the sky from the perspective of a window or facade. That covered portion is what we call its shading mask. Horizontal louvers provide the largest shading mask against high-angle sunlight for south-facing facade during midday hours. Vertical fins provide the largest shading mask against low-angle sunlight for east and west-facing facades during sunrise and sunset hours. Eggcrate shading devices combine horizontal louvers and vertical fins and offer the most shading mask across the day from sunrise through sunset hours. On this slide, we see a range of different shading device types and how each one affects sunlight. The diagrams categorize examples like horizontal overhangs, vertical fins, and combined Eggcrate shading devices, each paired with a sun path diagram and shading masks. Shading mask shows what portion of the sun's trajectory that shading device blocks. Shading mask diagrams highlight the time of the day or year when overheating or underheating is a risk. Designers can evaluate which device best blocks the unwanted sun or admits the wanted sun. By selecting a device with the right shading mask for the climate, we can control heat and glare while still welcoming in natural daylight. This slide provides a case study that puts these principles into practice. The Tamedia head office in Zurich, 2013. The building shows how the building form, facade systems, and timber structures work together to balance solar controls, daylighting, and natural ventilation. The building perimeter features an interstitial space created by the exterior glass facade and interior glass partitions, supported by timber structures. This interstitial space filters harsh sunlight and maximizes daylight penetration. The facade also incorporates operable glass panels to let in fresh air. The project shows an office building that stays bright and transparent without sacrificing comfort by embedding shading screens and ventilation capability right into its form and facade design. The next example is the SpareBank building in Stavanger, Norway, 2019. The building form consists of a recessed storefront beneath a glass curtain wall mass above. The recessed storefront regulates solar gain while providing visual transparency and public access at street level. The building integrates a large multi-story atrium enclosed with a sloping glass skylight supported by wooden structures. This atrium funnels daylight down through the center of the building, and all office levels receive ample daylight. In addition to daylighting, the atrium also facilitates natural ventilation through the stack effect. Outdoor cooler air is drawn in at the lower levels, and stale, warm air rises and is vented out through the top level. This project exemplifies that building form and space organization harness natural light and airflow, creating comfortable and sustainable environment inside with less reliance on mechanical interventions. Our next case is the Freemen School Indoor Swimming Pool in London, 2017, which tackles the dual challenges of daylighting a pool and controlling its humidity. The slide on the right includes a few small diagrams outlining the design approach. For instance, the pool hall is partially sunk into the ground and nestled among existing trees on the site. The roof is tilted for water collection while giving structural stiffness to the arching timber portal frame. The timber structures allow for column-free, large-span space. Side lighting from the transparent storefront illuminates the space and reduces artificial lighting demand. Transparency also allows the users to visually connect with surrounding landscape while also allowing views from the public into space. The slide now highlights an innovative facade system from Japan called BioSkin, 2011. The images illustrate how this high-tech cladding uses water to cool the building. Rainwater is collected, stored, and then pumped through a network of thin, porous ceramic pipes that run down the building's exterior, those ceramic tubes you see in the photos. On a hot day, water slowly seeps through these pipes and evaporates into the air, which cools the surrounding area and the facade, much like how sweating cools your skin. The balcony space, surrounded by the grid of ceramic tubes, further controls solar gain and microclimate, all while maintaining daylight and visibility for the occupants inside. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future.